Welcome everybody to today's FDTD Satellite Applications webinar. Today we're very happy to have Peter Banakis and Brooke Tabor from NWS WFO Burlington, Vermont. And the title of their presentation is a Satellite and Radar-Based Analysis of the 26 March 2021 Middlebury, Vermont EF1 Tornado Environment. Next slide. Just a reminder that all these webinars are recorded and available on visit web pages at the URL shown here. Also, we're looking for volunteers. If you have any interesting operational example to show that showed some utility of satellite, please go ahead and contact myself, Dan Bicus, or Scott Lindstrom. Next slide. We'll have about 25 minutes or so for our presenters today. If you have questions, send them via the questions in the webinar. We'll also have a phone Q&A at the end. So we'll be done by approximately 18:30 UTC. Just remember, do not press hold and mute when you're not speaking. At this time, we'll turn it over to Pete.
Thanks so much, Dan. It's a pleasure to speak with everyone today. Again, I'm Pete Banakis, the Science and Operations Officer here at Burlington. And myself and Brooke Tabor, who's a lead forecaster at the office in Burlington, will be presenting to you today on this rare tornadic storm that we had this past March. So the overview of what we'll be discussing, we'll jump right into the satellite analysis, starting with the GOES data. We'll look at the 7.3 micron low-level water vapor imagery, 10.3 micron clean IR imagery, and then the 0.47 micron visible or blue band imagery. We then want to discuss some experimental advected layer precipitable water products that are available via the polar orbiters. We'll then get into a synoptic and mesoscale review of the event. There was an elevated mixed layer present in this case. We want to discuss that along with some soundings and the SPC mesoanalysis. And then I'll turn things over to Brooke to describe the upper air pattern and the low and deep layer shear parameters. He'll look at some dual pole radar imagery, and our office conducted a damage survey. So we'll have a brief overview of that at the end. So again, this was a rare tornado. In fact, it's the earliest one we know of on record in the state of Vermont. There's never been a March tornado going back to 1950. And this was basically a QLCS event. We had a line of storms form east of Lake Ontario with the first wind damage reports occurring around 15Z. The line moved across the Adirondacks and strengthened in the Champlain Valley, producing that EF1 tornado around 1740Z in the Middlebury area. We had wind damage continue through central Vermont, right around Montpelier, before decreasing in intensity pretty quickly as the storms moved out of the instability axis. So here's the low-level water vapor imagery across the CONUS, and there's two main features to point out. We see this ejecting shortwave from New Mexico and the Southern Plains up into the Northeast. And at the same time, you'll see this narrow dry slot that develops out ahead of the main vort and comes right across New York and Vermont. As we loop this again, I want to draw your attention to the Mexican plateau. During the day on the 25th, some really warm brightness temperatures form associated with a deep mix layer that ends up getting entrained in some very strong southwesterly flow out ahead of the trough and becoming an elevated mix layer and being in place just in advance of the strong forcing that we had on the 26th. So that's kind of the broad overview of what we were dealing with. So the shortwave trough was quite vigorous, and the background flow was also unusually strong, as we'll see with some of the shear parameters in a bit. So here's the Albany Sounding at 12Z. And I want to particularly draw your attention to this layer of steep lapse rates between about 850 millibars and 650 millibars. What we see, the lapse rates were nearly dry adiabatic in that layer, and likewise the dew points are very close to a mixing ratio line. So this is the remnant elevated mixed layer that was advected in the strong southwesterly flow. You can see within that layer about 50 knots of southwesterly flow that morning. at 750 millibars, so quite strong on the winds as well. Boundary layer is not particularly moist, but as we saw some daytime heating, that layer of steep lapse rates was helping with our buoyancy. That really wouldn't have been present otherwise if we had more average lapse rates. So the elevated mixed layer definitely played a role in how robust the convection was able to get that afternoon. This is just a quick look at the Namm 47 to 500 millibar lapse rates. And again, in this loop, we can see the reddish colors and the whitish colors coming out from the Mexican plateau. That's the elevated mixed layer coming out. But as usual with the models, they have a tough time holding on to the steep lapse rates due to the parameterization schemes. The main point being that you really want to monitor your satellite products to look at the long transport of things like moist layers and elevated mixed layers, because the models don't always do the best job. We see some indication of the steep lapse rates persisting, but not quite as close to reality as we saw in the Albany Sounding. So I do want to point out the Advected layer precipitable water product, which is experimental. It's analogous to the total, I should say, precipitable water, but we're looking within 4 distinct layers. So you can look at this product from the surface to 850, 850 to 700, 7 to 500, and 500, 300 millibars. This is based on microwave instruments available on 7 polar orbiting satellites. And the advantage there is that we get a quantitative measurement of the moisture in each of those 4 distinct layers. So unlike a infrared-based product where you have more of a quantitative or qualitative measurement based on brightness temperatures, we're actually able to quantify how much moisture is available in each of the layers. So this is using the NOAA microwave integrated retrieval system, and it's produced on an hourly grid at a 16-kilometer resolution, and it's using the GFS winds to help with the advection as well. The microwave sensors can see through clouds and do retrievals within clouds, but not in areas of precipitation. So in the following slide, you'll see areas that are masked out in a black color where it is precipitating. And special thanks to Dan and Sheldon for providing the following slide. And obviously this is almost a hemispheric view of what the ALPW product looks like. So at the surface to 850 millibars, of course, we have the richest moisture. You see, especially in the tropics, these really bright colors associated with the color table down here. Again, the quantitative amounts of moisture available in millimeters. And ahead of, troughs, as you would expect, you do see these meridional plumes of moisture being advected northward. And the same was true here. This is for about the 10-hour period before the occurrence of the tornado. And you do see the moisture plume extending northward ahead of the shortwave trough that's moving from the eastern Great Lakes into New York at this time. And if you look a little further aloft at 850 to 700 millibars, you do see that narrow dry slot associated with the elevated mixed layer quickly propagating through the region. And that dry slot's a little bit wider here between 700 and 500 millibars. And then I do like this product also for the upper troposphere. You can really make out your PV features quite well. So your upper vort maxes is really good for tracing those if you look in the upper troposphere. So definitely a good way if you're trying to track, again, moisture plumes and elevated mixed layers over long distances. This is just a 10-hour loop, but you can certainly loop it over a couple of days and see some really interesting features that way. Again, this is an experimental product at the moment. It's planned for the satellite broadcast network delivery in 2023, but until then, you can pull it in through the LDM into AWIPS, and you can contact Dan Bykos at his email if you'd like to receive the data, as we've done here in Burlington. And it's also available online for those that aren't in the Weather Service, or if you're teleworking at the URL that's listed here on the screen. So we did do some confirmation using the GDAS data in the NOAA high split model that sort of confirms that the air that was over Middlebury around 17Z that day on the 26th originated from the plateau of northern Mexico. And likewise, the SPC mesoanalysis, even though it's based on the RAP, you do see a pocket of some steep lapse rates that were present around 17Z, exceeding 7 Celsius per kilometer from 7 to 500 millibars right over the Middlebury area. And that's co-located with the low-level moist axis, where we had dew points right around 60 degrees or so in the vicinity of the tornado. This is the visible satellite imagery, and a few interesting features here. We did have a warm front early in the morning moving northeastward across northern New York and Vermont, and you can see the convective nature of the clouds associated with the warm front, and there was some elevated convection connected to that warm front early in the day. And then you can see the vigorous mid-level vort coming across Lake Ontario, actually moving quite rapidly eastward. And this is what's going to force the convection. And out ahead of that, you do see this narrow dry slot, which resulted in some surface-based heating and surface-based instability. And at this point, you can see the development of some deeper surface-based convection across the Adirondacks. And this is really going to take off here as it moves into Vermont and produce what ended up being our tornadic storm in the Middlebury area. So the clean IR imagery, the 10.3 micron, showing much the same. You can see some of the deeper cloud tops associated with the warm advection, the warm front. And then as we see the shortwave trough come out during the late morning and early afternoon hours east of Lake Ontario, you'll see a gradual cooling of the cloud tops as the convection deepened and became more surface-based through time. And especially as this moves into the Champlain Valley and starts to feel Cape values probably between 1,000 and 1,500. That's when we had our best storm there, right at the end of the loop. So in summary, on some of the satellite data from the GOES products, well-defined clearing helped to warm the surface temperatures. The boundary layer temperatures did get into the 60s, and that was able to enhance instability, especially with the steep lapse rates present in the mid-levels. By 1:39 p.m., about an hour after the first image, the middle image shows the deep convection with the overshooting tops near Middlebury, and the IR satellite, of course, showing the cloud top cooling, which is a good indication of the strengthening convection as well. So here's a look at the surface analysis. It was a rather narrow warm sector, and again, you can see temperatures in the warm sector had warmed into the mid to upper 60s with dew points in the upper 50s to around 60, and then some strong cold advection behind the cold front here across central and western New York. And on the right image, we see the 3-hour change in surface-based Cape. So you can see that destabilization that was occurring from the lower Hudson Valley northward through the capital region of New York and into western Vermont, where you had a rapid increase in Cape, several hundred joules per kilogram, but it was sufficient to get some severe weather. And then, of course, a decrease in Cape going on behind the cold front as well. And likewise, again, from the SPC mesoanalysis, you can see the surface-based Cape values shown here between about 500 and 1,000 joules per kilogram. And if you want surface-based storms, you need the steep low-level lapse rates. And that was developing within the dry slot here at this time. You can see, especially over the Catskills, this 8 to 8.5 Celsius per kilometer in the lowest 3 kilometers. And that axis of some steeper low-level lapse rates extending northward into western Vermont gave us an indication that indeed this activity was becoming surface-based as it was moving eastward from the Adirondacks. This is a meteogram for Middlebury that we put together, and a few things of note. Early in the morning around 11Z, you see the moisture was really already in place, which is a good thing. Sometimes we don't have the moisture early in the day, or we're expecting a rapid moisture return, and oftentimes that ends up producing a lot of stratus clouds, over a boundary layer that's maybe not that warm, a lot of overrunning. But in this case, we already had dew points in the mid 50s. And temperatures, you can see, were also in the mid to upper 50s. And then after about 16Z, we got into that dry slot, and temperatures increased to about 67 degrees was the max that day. Dew points got up to about 60. Here's the time of the tornado here, again, about 1740Z. And at the same time, the winds were backing to southeasterly. We did have some wind gusts increasing to about 22 knots, probably some inflow into the convective line, seeing some indication of that. And then temperatures cooled a bit and then cooled further and dried out later in the afternoon as the cold front came through very late in the afternoon. This was probably the most representative model sounding we could find. This is a 6-hour forecast from the 3-kilometer Namm, valid for the Middlebury area. And again, we see at the surface 66 over 60. The surface-based capes around 1,500 joules per kilogram. Really nice wind profile, very strong winds. You can see in the upper right with the hodograph, we have a strongly cyclonically curved hodograph at low levels, and showing surface to 1 kilometer helicity values well in excess of 200 meters squared per second squared. So a very favorable environment for rotating storms, and just enough instability as well to pull off a tornadic storm here as well. So with that, I'm going to hand things over to Brooke to go into some of the upper air and the shear parameters.
Okay, thank you, Pete. And the first thing we're going to look at is the 250 millibar upper air analysis at 12Z on the 26th of March. And you can see here that we had a dual jet structure. We had the polar jet exiting across southern Canada at 100 to 125 knots. And then we have the subtropical jet, as Pete had described, helping not only advect some moisture, but also that dry layer that Pete was talking about, angling across the Ohio Valley into the mid-Atlantic, southern New England. And this dual jet structure helped to enhance the large-scale ascent across northern New York and Vermont to produce these thunderstorms in the afternoon. Looking at 500 millibars, we had a vigorous shortwave over the central Great Lakes. You can really see that on the analysis here by the X. In addition to that, we did have very strong mid-level winds as observed by the Albany of 50 knots at 500 millibars and extending down this jet maximum into the Ohio Valley where it was 60 to 85 knots. And as Pete had alluded to, this did help the deep layer, the 0 to 6 kilometer shear across our area. And if you look at the height fields closely across the Northeast, you can sort of see a upper level divergence in the height fields, and that would help promote deep scale synoptic lift. At 850 millibars, we had a closed contour of center of low pressure over the eastern Great Lakes. Once again, very strong wind fields. You can see by the packing of the height fields across the western Pennsylvania into the Ohio Valley region. And as this progressed eastward, this stronger wind max did angle up into central New York and impacted our central and southern Vermont CWA. And in addition, this really, these strong winds help to advect deeper moisture into the area. We're looking at dew points well into the surface dew points to near 60, but also 850 dew points, pretty anomalously strong, high, rich moisture coming up ahead of this trough. The shear parameters, this is from the SPC meso-analysis page at 17Z on March 26th. You can see in the lower left, we had surface to 6 kilometer bulk shear of anywhere from 50 to 80 knots. The deeper values or the stronger values of shear was closely tied to that jet maximum at 850 to 500 millibars. The star is the approximate location of Middlebury or the tornado. And then the surface to 1 kilometer storm relative helicity, as research has shown, any values over 100 are favorable for supercells and potential tornadic supercells. And in this case, we had values of around 200 near the Middlebury, Vermont area. It should be noted the higher values across the Northeast Kingdom into northern New England was mostly associated with the warm front as that was lifting north. We had an easterly component before the warm front and then shifting more to a westerly component. So pretty good low-level directional shear with that, just didn't have the instability with a very stable air mass to our north. The supercell composite and significant tornado parameter on the 26th at 17Z showed an axis of favorable supercell parameter up the Champlain Valley. That was the combination of shear and instability, as Pete had alluded to. We had anywhere from 5 to about 1,000 joules of cape, and that combined with pretty favorable shear parameters to produce this axis coming up the Champlain Valley. And very similar for the significant tornado parameter, We don't see indices like this very often because usually we're lacking some sort of ingredient for significant thunderstorms or tornadic thunderstorms. It's either the shear, we have the shear but not the instability, or we have the instability and not the shear. But to see values of 0.5 to 1, definitely a heads up in our analysis, and produces favorable conditions for tornadoes. The Storm Prediction Center day one outlook, I thought did a really good job. It had us in marginal. Once again, the question was how much surface heating we were going to get and instability associated with that dry slot. So not the most robust instability, but marginal we were outlooked for. And they did have us highlighted with the 2% outlook for tornado. And the wind threat was going to be the primary driving force with about 5%. So that outlook looked really well. As far as the products, Storm Prediction Center issued a severe thunderstorm watch just a little after 11 a.m. on the 26th, and that covered most of northern New York into Vermont, and definitely had the Middlebury, Vermont area covered in the watch. And then our local office here in Burlington issued a severe thunderstorm warning at just a little after 1 p.m. for a developing line of thunderstorms sort of coming across the Adirondacks and entering the Champlain Valley, where there was better moisture from that surface heating and the clouds that had broken up. So you can see here, this was the outline to our severe thunderstorm watch, or our severe thunderstorm warning. And our main primary threat was 60-mile-per-hour winds. Sort of a secondary threat was some small hail. The following is just a radar loop drawing your attention south of Cranberry Lake into the Newcomb area. Radar coverage across the Adirondacks is very limited, but as it enters the Champlain Valley, you can see how the convection becomes more robust, deeper, and intensifies, especially as it gets into the Champlain Valley and the Middlebury area. And then once again, we sort of lose the radar coverage on the eastern parts of Vermont due to the blockage from the Green Mountains, but it gives you an overall good idea of the evolution of the QLCS as it evolves from the eastern Adirondacks into the Champlain Valley. It becomes pretty well sampled and pretty robust in the Champlain Valley, Middlebury area. And if you look closely, you can sort of see how there's a comma head on the north end of the apex of the bow. And then it does go on to produce a little more damage in the Montpelier area before really falling apart across eastern Vermont. Taking a look at the rotational track, this is from 16Z to 20Z on March 26. You can see the storm of interest near just south of Watertown, moving towards the Newcomb area. And now the rotational velocity is starting to enhance in the Middlebury area as the storm is becoming stronger, and then continues to evolve from Middlebury to Montpelier. And then we really begin to lose the signal once again as it becomes pretty beam blocked and sort of falls apart, weakens east of Montpelier. Taking a look at now some closer up radar data from GR2 analysts. This is about 10 minutes prior to the tornado touchdown. The X on the image is the approximate location of the tornado, a couple miles northeast of Middlebury. The KCXX radar is about 35 miles to the north in this image here. And you have green, which is inbound velocity towards the radar, and red, which is outbound velocity away from the radar. At this time, it was mostly inbound dominated of 40 to 45 knots, real minimum outbound velocities of about 10 knots, creating rotational shear of about 30 knots, minimal, really a minimal meso at this time, given the radar data. Storm motions were anywhere from 250 to 260 at 40 to 45 knots, so basically from west to east. And that did make the radar sampling almost perpendicular to the beam in the Champlain Valley, adding to some radar complications when you have storms that are moving perpendicular to the beam and really capturing those stronger velocities. The reflectivity, I did adjust the reflectivity a little bit. Well, the 45 dBZs are shown in the red, 45 to 55 dBZs, just to highlight the higher reflectivity, as most of this was a low top line of showers and thunderstorms. but you can see the weak echo channeling on the back side of this, right at the apex of the bow here, so indicating a rear inflow jet. And our tornado occurred just on the northern side of the apex of the bow where you have that cyclonic curvature. Also to note is a fairly sharp reflectivity gradient on the forward flank, indicating the general idea of a pretty high wind threat. Moving ahead 5 minutes now, 1735, we're looking at about 5 minutes prior to tornado time, and that's outlined here in the X. Once again, the reflectivity on the right-hand image, you can see the real strong rear inflow jet with the weak echo channeling coming into just south of the Middlebury area, and you're just north of the apex of the bow of where the tornado occurred. And then on the velocity or storm relative velocity motion, not a lot of change. It's still a broad circulation. We're getting about 30 knots of rotational velocity here. Once again, that's a minimal meso. We're having stronger inbound winds of 40 to 45 knots and much weaker and poorly sampled outbound winds of about 10 knots or so. Moving ahead, one more at 1738, we were running sails, I believe, one cut. Not a lot has changed. You can see how the rear inflow jet now is sort of wrapping up and wrapping into the line of thunderstorms, and you can sort of see like a little comma head developing on the northern part of that apex of that bow. And this was very close to the tornado time. We did have a couple pictures of a funnel that was to the south and west of Middlebury at this time. So, and you can see how the couplet in the storm relative motion has tightened just a little bit. We're getting slightly better gate-to-gate shear with inbound and outbound velocities right over the Middlebury area. And I have to say that we were, you know, with our severe thunderstorm warning, we didn't put in the tornado possible tag, you know, but given how that couplet did increase right there, might have been a good idea. Looking at the spectrum width at the 0.5 degree slice, and local studies and also national studies have shown anytime where you have spectrum width greater than 20 knots does indicate the potential for a tornado. And spectrum width is just the variance of inbound and outbound velocities within a bin. So you can see how that's highlighted just to the northeast of Middlebury. Looking at the correlation coefficient at 1738, nothing really showing up just yet. Stepping ahead just a couple minutes, this is about a minute or two after the tornado had occurred. The better velocity, storm relative velocity couplet now is sort of shifted off to the northeast of Middlebury and has probably weakened at this time, not very well organized and no real gate-to-gate kind of shear. The base reflectivity is still showing kind of a linear line of convection with a sharp forward flank reflectivity gradient and a pretty good apex of a bow where that weak echo channeling is showing the stronger winds coming in associated with the rear inflow jet. And just north of that is the area of location where the tornado occurred with the X. Taking a look at the spectrum width once again on the left-hand image here, you can still see values of 20, 22 knots indicating the potential for a tornado. And then an interesting little signal showed up in the correlation coefficient. We did get some lower values indicating the potential for tornado debris signature. I did do a cross section and noticed that these extended up to about 3,500 feet above ground level. So there was some vertical continuity to that. One thing to point out, as the tornado was just on the ground very briefly, we started to lose the signal, especially east of this road here, 116, as it becomes very mountainous, and the terrain had really played an effect of that. And I think part of the terrain helped to produce this little spin up, as you had really strong winds going perpendicular into the terrain, and that acted as a blocking feature to help spin the cyclonic circulation to produce the tornado just northeast of Middlebury. But anyways, so this was the last image I had as the image radar became very diffuse and very disorganized moving forward. We did do a storm survey damage, and you can see that Based on our storm survey, we had about a length of 0.6 miles. At its greatest width, it was about 75 yards wide. It was approximately on the ground for 1 minute. It did produce a funnel on the west side of Middlebury, which in this image is to the southwest. We did have 4 homes damaged and unfortunately 2 injuries. And based on our damage, we rated it at EF1, and we determined the max sustained winds were around 110 miles per hour. And you can see here by the little upside down triangles, the green EF1 damage and the blue are EF0 damage. And Painter Road was sort of our main point of contact, or our main area of viewing, as you will see in these pictures coming up. So once again, the image on the left is showing our damage survey and the track. And then here are some aerial photos courtesy of the University of Vermont. And just to give you an orientation, we're sort of looking south here. This is Painter Road. Here's some of the houses that were damaged south of Painter Road in this area over here. And then as you're looking northeast, you can see there was a farmstead that was damaged, and there was quite a sustained damage to this structure here, which we'll have a zoomed in picture in just a minute. This is still looking, now we're switching our angle, looking a little more northeast. Painter Road would be to our south now, and this is the same barn in this area here. And they did sustain quite a bit of roof damage, and there was quite a bit of tree damage to this tree farm. A little bit closer up, this was one of the houses that sustained some damage south of Painter Road, uprooted trees, quite a few trees knocked down or sheared apart. And this was probably the most structural damage that we have seen in a while. This was a attached garage to this part of the house, and then the strong winds blew it to the east and really detached it and shifted it about 20 feet to the east. And the winds were strong enough to overturn this car. So pretty impressive damage, especially for our area, and especially when you consider it was late March. Unfortunately, there was other damage. You can see this part of this roof was torn off. These trees were snapped off. I'm not too unsure about the power lines, as this was taken 2 weeks later, and I'm not sure if these high tension power lines were damaged or not. But with that, we'll end that and open it up to any questions that anybody may have for Peter or I.
Okay, for the questions, you can either submit a question to the chat box, the question box, or I will go ahead and unmute everybody. So if you'd like to speak up, you can do that now.
Hi, this is Scott, and I have a question. Well, 2 questions. Well, one question and a comment. I'll start with a comment first. I was wondering maybe what Newcap Sounding showed, but then I looked at the Newcap's overpass was just about the time of the tornado. So, you know, oh well, I don't think that would have been very useful. But I was wondering about the electrical activity with the storm, and if you were able to use GLM data with it and see any kind of signal with the change in lightning as the convection started to spawn the tornado.
Yeah, thank you, Scott. That's a great question. The overall lightning activity was pretty minimum with this line, as most of the convection had a hard time reaching up to about 20 to 25,000 feet. It was highly sheared given the environment, and the lack of instability really didn't help to promote deep convective updrafts as you would normally see. So if I can remember right, I didn't work the event, but I did look at the lightning, and it was very sporadic at best, and we didn't really see any kind of signals of lightning activity jumps or anything like that.
Thanks.
Okay, any other questions? Okay, well, I'm not hearing any other questions. So at this time, we want to thank Pete and Brooke for the great presentation today. And we'll have a recording of this presentation posted by tomorrow. Thanks, everybody, and have a great day.
Thank you.